Oh, Pascal's triangle. He's so pretty. Okay, check this dude out. You always start with a 1, 1, 1. Okay, at the top. Okay, and then after that, really cool stuff starts happening. You just have to add the two numbers above it. The outsides are always going to be 1. And then, like this guy right here, you would add the two top numbers to get it. So it would be a 2. All right, so outside starts with a 1. If I add these two, I get a 3. And if I add these two, I also get a 3. Oh, what a cool little pattern thing happening here. And then 1 goes on the outside. So 1 goes on the outside, I add these, I get 4. Add these, I get 6. Add these, I get 4. And then on the outside, we have a 1. Ooh, what a cool pattern. All right, and then we get a 1, and then we get a 5. And then we get a 10, and then we get a 10, and then we get a 5, and then we get a 1. 1, 6, 15, 20, 15, 6, and now. You guys notice a pattern? Yeah, I know you guys notice that pattern. It's a pretty obvious pattern. And the next one is 1, 7, 20 now. And then we have 35. And then we have 35, 20 now. 6, nope, not 6, 7. And then now. All right. Now, with the binomial theorem, we're going to be using Pascal's triangle. And so when you're looking at each of these rows, what's with my arrows? I look at this row, look at this row, look at this row, look at this row, look at this row. You want to think of this as row 0, which we don't really care about. This is row 1, which again, we don't really care about. This is when we start counting. We care this is row 2, this is row 3, this is row 4, this is going to be row 5, so on and so forth. You can kind of see it too just by looking at these dudes right here. That's how you know which row is what. Okay, but Pascal's triangle is really rad. If you spend a lot of time with Pascal's triangle, you can find a lot of patterns, which is kind of crazy and cool and fun. Now, look at these rows. Let's start with row 2, because that's when things start looking cool. We don't notice much with row 0 and 1. So let's say if we had y or x plus y raised to the second power. You guys know how to do this. It'd be x plus y times x plus y. And if you do that, you'll get x squared, right? X times x is x squared. Then you go x times y, which is xy. And then you go y times x, which is also xy. It's alphabetical order. I put the x before the y. And then y times y is y squared. And then if I add these two like terms together, we get x plus 2xy plus y squared. Oops, I said x squared. And if you look and notice, you'll notice the coefficient is 1, then 2, then 1. And look at that. 1, 2, and then 1. Yeah, that's right. The power of 2, we get 1, 2, 1 as our leading coefficients. Now, I chose my binomial carefully, guys. There's no coefficients in front of them except for a 1, which makes the Pascal triangle thing very, very obvious. So here, check this out. Check this dude out. All right, so let's go x plus y to the third power. Okay, that's the same as x plus y squared times x plus y to 1. And I'm doing that just so I can just copy this right here. So then if I'm copying that right there, I get 1. No, that's not right, the 1. X squared plus 2xy plus y squared. And we're multiplying that by x plus y. Okay, so this is x plus y squared. And now I have to multiply by x plus y one more time to do it to the third power. Now let's see what happens. X squared times x is going to be x to the third. X squared times y is going to be x squared y. All right, next dude. We have 2xy. 2xy times x is going to be 2x squared y. Then 2xy times y will be 2x y squared plus. All right, one more. Y squared times x would be xy squared. Then we have y squared times y would be y squared. Combining like terms, we can add this dude with this dude. All right, that would be 3. Did I do that right? See, how did I get that? Yeah, I did do that one right. So that would be x to the third plus 3x squared y. And then we have these as like terms also. So that's also going to be a 3xy squared. And then we have our y to the third. Now take notice of our leading coefficients. Yet again, we have 1, 3, 3, and 1. Look at that. When we do the third power, we get 1, 3, 3, and 1. So what if we follow this pattern using Pascal's triangle, we get a lot of shortcuts here. Okay, let me show you. If we had 5, a fifth power, Ooh, fifth power. Okay, we're going to have 6 terms. I don't know if you noticed that. If you look over here, when we raised to the second power, we ended with 1, 2, 3 terms. When we raised to the third power, we ended with 1, 2, 3, 4 terms. So we end with n plus 1, or just adding 1 to the power that you're raising it to. This is the binomial theorem. And so we have 1, 2, 3, probably around the room, 4, 5, and then one more. Oh, cool. I didn't run out of room. I had to write on the board there. So we have, wait, is that right? See, 1, 2, 3, 4, 5, 6. Yeah, so 6 terms. Okay, and if we throw in our leading coefficients, it's 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, and then 5, and then 1. So all our leading coefficients are there. And then we know that this is going to be an x, and this is going to be a y, this is going to be an x, this is going to be a y, this is going to be an x, this is going to be a y, this is going to be an x, this is going to be a y, this is going to be an x, this is going to be a y, this is going to be an x, this is going to be a y. Okay, now we just have to do the powers. Ooh, the powers, what? What? Yeah, the powers. Okay, so the x is going to count down, the first term in our binomial. So it's going to start with a 5, and then go 4, 3, 2, 1, and then 0. 0 means, anything raised to 0 power is 1, so that's just going to cancel out that dude. He's going to be a 1. And then we count up on the y value. So 0, 1, 2, 3, 4, and then finally 5 on our y value. So now if I simplify my results, all my stuff, we get x to the 5th for our first term. Right? For our second term, we get 5, x to the 4th, and then y. Plus, this one, we're going to get 10, x to the 3rd. I know, guys, this is really rad right now, huh? And then for our fourth term, we get 10, x to the 2nd, y to the 3rd. Ooh, we see the pattern. I hope you see the pattern. And then we have 5x, y to the 4th, 5x, y to the 4th. And then our last one is going to be 1 y to the 5th. Oh, so pretty. And that's right, guys. That's right. Now, what would you do? What would you do if we had like a 2 right here? Okay, so this term isn't an x, it's a 2x. That means you have to plug 2 next to all these x's, and that's going to change your leading coefficients, because 2x to the 5th, that's like 2 times 2 times 2 times 2 times 2. That's going to give us leading coefficient. So it's going to change. That number is going to multiply to 1. You're going to change the leading coefficient there. Same with this. That's 2x raised to the 4th. 2 to the 4th is 2 times 2 times 2 times 2. We're going to take that number and multiply it times the 5, and that would change that. Okay, so now our result, because this would have a 2 on it, then our result is not going to you're not going to see clearly the Pascal's triangle when you're finished with it. Right now you can, because we do not have a 2 in front of the x. We just have an x, a 1x. And same goes for this guy. Now, just a quick note, if this said minus and this said 3 right here, then you would put a negative 3y right here, not a positive 3y. We would change this to addition and then make that a negative 3y, and we would plug that into all those things. So anyways, that's Pascal's triangle. One of the cool things we can use Pascal's triangle for is the binomial theorem.